Hey, Rouse. For lesson 7.1 on linear combinations, it should feel pretty familiar. It should feel like just adding scalar multiples of vectors together. But our focus is more on discovering if it's possible to write one vector as the resultant of scalar multiples of the addition of the scalar multiples of the other two. I want to walk through example 2. I'm going to try it in a different way and we'll see how terrible it turns out. I know the solution that I planned in the lesson worked out with relatively nice integers, or didn't work out with integers. So I'll take another run through it just to show you that it doesn't matter in what order you choose to work. So let's try answering the question, are these three vectors coplanar? And I need to go out of my way to say coplanar vectors here because of our sort of ambiguous notation. 3 points, any 3 points, are going to be coplanar. Just a quick review here. What we mean by coplanar is here's a plane, and I can define a plane by 3 points. That material was planned for Unit 8, and I guess we won't have time for that. But yeah, what we're looking at here is we have 3 vectors, and we're wondering, are these 3 vectors, do they lie in the same plane? And the argument goes that if one vector lies in the same plane as the other two, then there should be some way of adding linear multiples or a linear combination, scalar multiples of the first two to get the third. Okay. So what I am going to do is I am going to see if it can be done. In the printed lesson, I set this vector to be a linear combination of those two, which I think made sense just given the size of these coefficients. Things would probably work out nicer a little bit. This time through, I'm going to try seeing if I can write the vector -1, 2, 3 as a linear combination of these two. Now, there's a very tiny little word here that we've been missing on a couple of our quizzes and tests. I'm not going to say this is equal to this plus a scalar multiple of this plus a scalar multiple of this. It's a very, very small word, but it is very important. I am going to say I'm going to set -1, 2, 3 to be equal to, I don't know, a 4, 1, -2. Are those the same? Yeah, these are the same coefficients I used in the lesson, but they'll be different values because I'm doing this in a different way. Plus b times -14, -1, 16. This is very, very important because I don't know if this is true. I am setting it to be true, and I will see if I can find a solution that satisfies all of the conditions in this, all 3 of the equations that this will generate. If it does, then I will conclude that yes, it can be done. If I find a conclusion, then I see that this was my, not mistake, but where the contradiction occurs, I suppose. Okay? So include that wording right there. And this means that for the sum of vectors to be equal to another vector, their components must be equal. So let's just say, without showing the combination of these scalar multiples here, let's just say that -1 would have to equal 4a minus 14b, and 2 would have to equal a minus b, and 3 would have to equal -2a plus 16b. Now, this looks like an overload of information. I have 2 unknowns. I should only require 2 equations to solve for those 2 unknowns. And that puts some students into a false sense of security here. We actually have 3 equations, and if I'm going to try to find a solution to this system, that solution would have to satisfy all 3 equations. Okay. It's kind of up to me to make sure that I check in the third equation. Sometimes students will use 2 equations to solve for an unknown and then just substitute it into the third to find the other unknown and think that they've used all equations. But if you check those solutions, they won't work for all 3 equations. I'm going to make the choice to work with, let's see, label this equation 1, equation 2, and equation 3. I'm going to work with equation 2 and 3. I'm probably going to eliminate a this time through. And then I'll solve for b in equation 2 and 3, or 3, and then I'll check my solution in equation 1 and see if it satisfies or not. And if you've read the lesson already, you know that this isn't going to work out, but let's find out. Sorry. Make sure you're communicating your steps here. I am going to take equation number 2 and double it. 2 times equation number 2 will give me 4 equals 2a minus 2b. I'll call that equation number 4. And now I'm going to eliminate a by doing equation 3 plus equation 4. That'll give me, unfortunate with these numbers here, this 3 plus 4 is going to be 7. That's just a coincidence that that's equation 3 plus equation 4. My a terms will eliminate, and that will give me 14b. Good. I can now solve for b. b will equal 1/2. Let's call this statement 5, and I'm going to substitute 5 into. Now, I don't need to check statement 5 in equation 4 and 3. Equation 4 and 3, and because equation 4 came from equation 2 and equation 2, all three of these, logically, they have to give me the same value of a, unless I made a mistake. What's not guaranteed is that it would give me the same value of a if I substituted into equation 1, which I haven't used yet. Let's see what happens. I'm going to put statement number 5 or equation number 5 into, what's the easiest spot? How about, I was going to do 2 because it was already isolated. Yeah, well, I will. I don't want you to be confused here and say, well, wait, I thought you're using the system with equation 3 and equation 4. Let's keep in mind equation 4 is in agreement with equation 2. It is a scalar multiple of equation 2. It has the same solutions, the exact same solutions as equation 2. So putting statement 5 into equation 2 gives me 2 equals a minus 1/2. I add 1/2 to both sides, and I get 4/2, 5/2. Okay. Now, what I have discovered, if you notice which equations I've used equations, let's get a different color here, 2 and, I don't know, maybe I want a symbol, 2 and 3. Equation 2 comes from equating my y components. So that's the omega, omega, omega. And equation 3 comes from equating my z components, gamma, gamma, gamma. So I haven't solved this system yet. I've figured out that I can get the vector 2, 3 by adding linear combinations of the vector 1, -2 and -1, 16. That should be obvious. 2, 3 is definitely coplanar with 1, -2 and -1, 16. And these vectors aren't parallel to each other. They're not collinear, which means that those two two-dimensional vectors span a two-dimensional surface, and I should be able to get anywhere. What I'm not sure about is when I add 5/2 of this vector and 1/2 of this vector, am I going to end up with an x coordinate or an x component, sorry, of -1? The easiest way to check this isn't to resolve the system, but just to take this value, you substituted this value, you substituted this value into equation 2, which was a member of this system of equations. Now just substitute that value into equation 1. So I'm going to communicate. I'm going to put 5 into 1, and that'll give me -1 equals 4a minus 14 multiplied by 1/2. That's -1 equals 4a minus 7. I add 7 to both sides. I get a equals 3/2. These do not agree with each other. I think it's up to me to point out that this is a contradiction. And that means that -1, 2, 3 cannot be written as, I'll write it out in English because we're going to want to review this for lesson 7.2. Anyways, -1, 2, 3 cannot be written as a linear combination of the vector 4, 1, -2, and, -14, -1, 16. This means that by adding linear combinations of these two vectors, let's pretend that these two vectors actually exist on my page. I've found the plane that these two vectors will span here. The two-dimensional space, two-dimensional surface that they will define. I could get anywhere on that plane by adding linear combinations of that vector, but I've discovered that I can't get to this vector, and that means that that vector lies somewhere outside of that plane. Not necessarily mutually perpendicular to the plane, but definitely outside of that plane. Right? And this means that the vectors, you can say, are not coplanar. A cooler version of that is non-coplanar. Much, much cooler. Okay. It's the language that is going to be challenging here and will definitely become a challenge in 7.2. The algebra should be a review of solving systems from grade 10. And I strongly recommend that you practice using elimination instead of substitution. It still might not be the most efficient approach to every single homework question, but it is the best approach in general.